Hi, my name is Muhammad Tariq, and in this lecture, we will talk about binary trees. How binary tree works, what is the structure of binary tree, and what are different types of binary trees we have. This is an introductory lecture, and we will try to explore the basics of binary tree in this lecture. And in the subsequent videos, we will explore more about binary trees, their advanced features, their operations. So, let's get started. So the overview is the basic structure of binary tree, the construction, how it can be constructed, important terminologies related to binary trees, size and depth, and computation of the height and the total number of nodes that we have in the binary trees and how we can get those using some formulas. And finally, we will see the binary search tree, which is the basic for implementation of the advanced binary trees. So if we look at this simple figure, here we have a natural tree, and so this is a basic binary. This is a basic tree, a natural tree, and as we know, every tree has a root. Every tree has a root. This is a root, and this is a starting point of a tree. And then we have some leaves, right? I'm representing leaves with L, and there are some fruits. Some trees have fruits, some trees don't, and I'm representing with F. So in the same way, the tree that we have in computer science follows the same structure and rules that a natural tree has. So we have a root, and we call it the root node. I am representing with Rn, root node, and then we have some branches, and these are the branches, and further when they grows, so we have some further nodes. So these are further the nodes of those branches. And as you can see here, it's a simple tree structure that follows the same one that we have in a natural tree, but it's an upside down structure. Here we have a root at the bottom, and in our trees we have a root at the top. So let's see further what other properties we have. So the basic structure is a tree is an abstract data type, and one entry point, that's the root. So here we have a root. This is the entry point, the starting point of a tree structure. Each node is either a leaf or an internal node. So as you can see here, we have total 5 nodes. Let's say 1, 2, 3, 4, and 5. So these are the leaf nodes. These are leaf nodes. Why we call them leaf nodes? Because they don't have any children associated with them. As with this one, this is an internal node. I'm representing with IN. So this node, the node number 2, has 2 children. One is on left hand side and one is on right hand side. So the leaf nodes are the one which do not have any children, and internal nodes are the one. The root also is internal node because it also has 2 children. So the internal nodes are the one who have some children associated with them. An internal node has one or more children. It can have one or more children. An internal node is said to be parent of its child. So we can say here, let me make it a bit cleaner. So we can say here that this node is a parent for these 2 nodes. And these 2 nodes are the children of this node, right? Okay, so the binary tree is something structured like this. So we have a root a node, which is the top node, and then the root node contains references for their children. So as you can see here, the root node, which is A, has a reference of its left child and has a reference for its right child also. In the same way, the node B contains the reference for its left child and contains the reference for its right child. On the other hand, the node C only has the right child but do not have any left child. So this node or this left reference, we will call them null. It's a null reference. So this is the basic structure of a binary tree. Okay, now let's see some parts of binary tree. A binary tree is composed of zero or more nodes. As you can see here, these are all the nodes. And this f is a value, this b and g, these are the values. These can be a string, right? This can be a string, integer, or this can be an object, right? This can be an object also, and we will see this later. Okay, so each node contains a value of some sort, a reference or pointer to the left child, or it can be null, a reference or pointer to the right child, or it can be null. So as you can see here, the root f has a reference of its child b and also its child g, and likewise b has a reference of child a and reference of child d. But the leaf nodes like c, they do not have any reference. A binary tree may be empty, contains no nodes. If not empty, a binary tree has a root node. Every node in the binary tree is reachable from the root node by a unique path. Now, what does it mean? Let's try to understand this. So, for example, if I have this tree, this is an example tree, and I want to get to the node E. So, what I will do, I'll start from the root node, I'll start from here, and how can I get to E? What path I'll have to follow to get to E? So I'll from A I'll go to B, from B I'll go to D, and from D I'll reach E. So and if I want to get to H, so what path I'll have to follow? The path would be F to G, G to I, and I to H. So if I want to get to any node, every path will be unique path, right? For first one we can say the path is F, B, D, and E. For second one, we can say the path will be F, G, I, and H, right? Here my starting point was E, and my ending node or my target node was E, and in the second time, my target node was E. A node with no left child and no right child is called leaf, as we already have discussed. Okay, now see some of the terminologies of binary tree. We have covered most of the terminologies. Let's just review them. A node is a point in a tree. Each node has a label, value at each node. So in the figure, each circle contains a node. So each circle contains a node, and these are some values. And it can be, as I discussed earlier, it can be numeric value, it can be an object, it can be anything, right? Node, sorry, root, a root at the top, the node at the top. Every tree has one root. In the figure, f is the root node. In the figure, here we can see f is the root node. Parent, the node that is directly above a node. In the figure, the node D is a parent of node C and E. It's the node D is a parent for C and E. Children, a node directly beneath the node. In the figure, the nodes C and E are the children nodes. So in the figure, nodes C and E are the children nodes. Inner nodes, a node with children. In the figure, nodes B, D, E, F, G, and I are the inner nodes. So B, D, G, F, and I, these are the inner nodes. Leaf nodes, a node with no children. In the figure, nodes A, C, and H. Node A, C, E, and H are leaves. A subtree, a node and all its descendant. So a subtree is here for F, all its descendant. So these all are descendants, and this whole is a subtree of F. So in the same way, on the right hand side, this whole tree, these all nodes are children of F, right? Likewise for B, this structure this structure is a subtree of B. So for G, this structure is subtree of G, right? So the subtree actually all the descendants of that node. Now let's see the size and depth of a tree. The size and depth of a binary tree is a number of nodes in it, right? So let's say if I try to count the number of nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the size in this of this tree is 12, right? The depth of a node is its distance from the root. So the depth is for the depth. Let's divide this tree in levels. These are levels, right? So we have the first level is the zero level. The root level is always the zero level. Level 0, level 1, level 2, level 3, and level 4. So we have total 4 levels here for this tree. For this tree, A is depth 0. So the A is a depth 0, and E is a depth 2. So here is node E, which is at depth 2. The depth of a binary tree is the depth of its deepest node. So the actual depth, if I want to calculate the depth of this binary tree, so I'll say 4 is the actual depth, because the deepest node is L, and which is the last node. So if I want to know the depth of any tree, so I will get the depth of the last node, and whatever the depth is, I'll call that one as a depth of the tree. That this tree has depth 4, right? Okay, now let's look at some of the types of the binary trees. Full binary tree. A full binary tree, sometimes proper binary tree, we can call them proper binary tree or two tree, is a tree in which every node other than the leaves has two children. So as you can see here, this is the leaf node. This is the leaf lab. These all are the leaf nodes. So other than those, every node has two children. So root has two children, this one and this one has two children, and all these four nodes have two children respectively. So this is a definition of a full binary tree. Now what is complete binary tree? In a complete binary tree, every level except possibly the last one is completely filled, and all the nodes in the last level are as far left as possible. It can have between 1 and 2h nodes at the last level h. So as we can see here, this is the last level, right? This is the last level, and every node above that is complete. So A has two nodes, B has two nodes, C has two nodes, and D has two nodes, E has two nodes, F only has one node, and G do not have any node. Okay, so the total number of nodes, which is 2 raised to power D plus 1 minus 1, where D is the depth of the tree. So if I want to know about total number of nodes of any tree, so I have a formula where 2d is the depth of the node, and with this formula I can get the total number of nodes of a tree. So for example, for this tree, let's say if I want to calculate the total number of nodes. So 2 raised to power d plus 1 minus 1. So what I'll say, what is the depth? Let's divide them into level. Let's Let me clean it first, and let now cleanly divide them into some levels. So it's level 0, level 1, level 2, and level 3. So 2 raised to power d plus 1 minus 1, and I can say 2 raised to power 3 plus 1 minus 1, which is equals to 2 raised to power 4 minus 1, and which is equals to 2 to the 4, 4 to the 8, 8 to the 16, 16 minus 1, which is equals to 15. Now let's count the number of elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Only 12. But because it is not a full tree, if we make it full, 1 here and 2 here, right here. So now it's 12, it's 13, 14, and 15. So with this formula, we can get the total number of nodes of a tree if we know the depth of the tree, right? Now the height of the tree. For the height of the tree, we have the formula log of n plus 1 minus 1, where n is the total number of nodes. Now with this formula, we know the total number of nodes of this tree is equals to 15. Now let's apply this formula to get the height. For example, if we don't know the height, in this case we know the height. That's how we got the total number of nodes. But let's, for the sake of understanding, let's say we do not know the height of a tree, but we know the total number of nodes. So how can we get the height of the tree? Log of n plus 1 minus 1. So log here, base is 2, right? Base is 2. N is 15 plus 1 minus 1, and log base 2 of 16 minus 1. Now how can we get the log of 16 with base 2? So we will multiply the number of times we could get to 16. 2 into 2 to the 4, 4 to the 8, 8 to the 16. So the total number of 2's, if when we count the total number of 2, we will get 4, right? 1, 2, 3, and 4. Total count is 4. So the answer is 4 minus 1, which is equals to 3. And the total, and the height of this tree we know is 3 also. 0, 1, 2, and 3, right? This is how we can calculate the depth, the height of the tree. We can also call them the depth, right? And we can also get the total number of nodes. Now let's look at the binary search tree. In computer science, binary search tree is sometimes called ordered or sorted binary trees, are a particular type of container, a data structure that stores items, right, such as numbers, names, and etc. in memory. A binary search tree is sorted if every node in the tree is larger than or equal to its left descendant. Its left descendant. It is smaller than or equal to its right descendant. Now, what does it mean? Let's see the structure. We have a node with the value 10, right? Which we have a root node. The left hand side of the root node is less than the root, and the right hand side is greater than the root, right? So the left hand side is less than the root, and right hand side is greater than the root. So in the same way, if we look at the root 15, the left hand side is again the less than the root, and right hand side is greater than the root. So we'll have to follow this rule to get the binary search tree. And most of our application are based on the binary search tree. When we look at the further um, trees, the advanced trees, they will follow the binary search tree rules. So this is a basic introduction of trees. So in this lecture, we saw the tree and its basic structure, the parts of binary trees, the terminologies used for binary trees, size and depth, the types of binary trees, the height computation and size computation, and binary search trees. Thank you.